Morning all. Today in this lecture, I will try to explain what is meant by Mossbauer spectra. Okay. In 1958, Rudolf Mossbauer discovered this or experimentally demonstrated this effect, and he got Nobel Prize for this experiment in 1961. What is Mossbauer spectra is all about? Suppose you have a radioactive element, a heavy element which is radioactive, then it is unstable. Through a radioactive process, it will decay to another element. And usually, in all radioactive decay, whether it is alpha decay or beta decay, the resultant nuclei will be in an excited state. And that nuclei will come to ground state via gamma ray emission. So, an alpha decay or beta decay, it will always associate with a gamma decay. So, when the excited element comes to the ground state, it will emit a gamma ray. And if there is a nearby similar nuclei, then this gamma ray can excite that nuclei from ground state to excited state. So there is two processes. One is the gamma ray emission, it is for gamma ray fluorescence. And using this gamma ray, similar nuclei in the ground state can excite. That is called resonant absorption. Okay, this is the things that is happening in Mossbauer spectra. Consider an example. It is cobalt 2757. It is a radioactive element, radioactive nuclei, which on electron capture becomes iron 57. The atomic number reduces by 1 because in electron capture, one of the proton in the nucleus converted to neutron. So the mass number remains the same, but due to the decrease in proton number, the atomic number reduces by 1. But the formed iron nuclei will be in the excited state, so it will emit a gamma ray to come to the ground state. This gamma ray can be absorbed by a neighboring iron nuclei, which is in the ground state, and can get excited. But in the actual case, the produced iron 57 nuclei will be in an excited state of 136 kilo electron volt. It will first emit a gamma ray to come to a state which is 14.4 kilo electron volt. Then it comes to ground state, that is 0 kilo electron volt state, by emitting a gamma ray. And this is the gamma ray that we are usually studied in the case of Mossbauer spectra. And it is of energy 14.4 kilo electron volt, and it is equivalent to 2.30 into 10 to the power minus 15 joules, and the corresponding frequency of radiation is 3.5 into 10 to the power 18 hertz. It is the gamma ray. It is in the gamma ray range of electromagnetic spectrum. So this is the one which we are used in Mossbauer spectra. Now the question is it possible to absorb this gamma ray by a nearby iron nuclei which is in the ground state? Okay, the answer is it is possible only when the source is moved. The source is kept stationary, then it is not possible by the second nuclei to absorb this gamma ray. Why? There are two possible reasons. The one is regarding the line width of emitted gamma ray. Okay. You consider the excited state of iron, that is the first excited state at 14.4 kilo electron volt. The lifetime of that state is about 1.5 into 10 to the power minus 7 seconds. Using uncertainty principle, you can calculate the energy width. Delta T is of the order of Planck's constant. So delta E, energy width will be of the order of 10 to the power minus 27 joules, and the corresponding frequency width will be 10 to the power 6 hertz. So a line at 3.5 into 10 to the power 18 hertz has a line width of around 10 to the power 6 hertz. That is a broadening of around 10 to the power 6 hertz. It is very small compared to the original frequency, or we can calculate the relative line width. It is delta nu by nu. It is 10 to the power minus 12 hertz. This relative line width in the case of Mossbauer spectra is very much smaller compared to the nuclear magnetic resonance spectra or the IR spectra, infrared spectra. Okay, their relative line widths are respectively 10 raised to minus 8 and 10 raised to minus 5. But here the relative line width is very small. That is, this is a very sharp emission. This gamma ray, the width of gamma ray is very small. Now, the second thing we have to consider is recoil effect. What is meant by recoil effect? When a nuclei in the excited states emit a gamma ray, that gamma ray moves forward with a high momentum. We can calculate the momentum using de Broglie relation. P is equal to h by lambda. Lambda is c by nu. So it is h nu by c. Since nu is very high, this momentum will be very high. Before decay, the nuclei was at rest. So when a high energy gamma ray is emitted from the nuclei, that nuclei must move backward in order to conserve the momentum. So to satisfy law of conservation of momentum, the nuclei will move backward. We can calculate the recoil velocity in the case of iron 57 for the emission of gamma ray with frequency 3.5 into 10 to the power 18 hertz. The recoil velocity is of the order of 10 to the power 2 meter per second. This is a very high velocity. 100 meter per second is the recoil velocity of nuclei. And we all know a moving source emits radiation and a stationary observer sees a shifted frequency. This phenomenon is called Doppler effect. That is, if you have a moving source and a stationary observer, the observer sees a radiation which is different than the emitted one. Due to the relative motion between observer and source, there will be a shift in the frequency. That shift is called Doppler shift. And the equation for Doppler shift is delta nu is nu v divided by c, where this nu and c are the frequency and velocity of the gamma ray radiation. That is, c is 3 into 10 to the power 8, velocity of electromagnetic radiation. V is the relative velocity between source and observer. If you calculate this Doppler shift for iron, you will get it as 10 to the power 12 hertz. Even though this shift is very small compared to the position of a line, that is 3.5 to 10 to the power 18, the shift is very small compared to that original radiation. But this shift is very high compared to the line width of that particular gamma ray emission. The line width of that gamma ray emission is only 10 raised to 6, but the frequency shift due to the Doppler effect is 10 to the power 12 hertz. Okay. So what Mossbauer did in order to obtain a resonant absorption, he used a solid crystal lattice to put the source to reduce recoil. That is, here the source is cobalt 57. On electron capture, it converts to iron 57, and that will emit the gamma rays. So the gamma ray source is actually the cobalt 57 nuclei. We can put the cobalt 57 nuclei in a cubic crystal lattice, say rhodium. It is a heavy element. It is a cubic lattice. You can put this cobalt nuclei in dilute proportion in the rhodium matrix. Then the total mass of that lattice will be very high. That will reduce the recoil velocity. That is the same as the case in the case of a gun that is kept in the shoulder to reduce the recoil effect. So, in order to increase the mass, you put the source in a solid crystal lattice. That will reduce the recoil velocity and that will reduce the frequency shift. That is one thing that Mossbauer did. Second thing is he kept all the source absorber, all this experimental setup in a very low temperature, that is in the liquid helium or liquid nitrogen temperature, to reduce the thermal motions of lattice, not to reduce the further recoil effects. While doing this too, Mossbauer could eliminate the or reduce the recoil effect to a very great extent. Then it is possible to observe the resonant absorption, but experimentally still there were no absorption, there were no resonant absorption while making these two changes. Okay, the reason is in source and in the absorber the ion will be in different environments. In the source it is kept in the rhodium lattice. The electronic environment of ion is different, but absorber material may be steel. In steel the ion has a different chemical environment. Due to this chemical environment, the energy levels of iron 57 will be shifted or will be split by small amounts. Okay, shifted means the 14.4 kilo electron volt I shown the first slides. The 14.4 kilo electron volt separation is for iron single atom. If it is in a matrix, if it is in a different chemical environment, this value may slightly change. Okay, that change may be very small, but there will be slight changes in this energy level separation depending on the chemical environment in which this iron atom sits. Okay, so depending on the chemical environment, there may be a slight shift in the energy levels. That maximum shift can be of the order of 10 to the power plus 8 hertz. 10 to the power 10 raised to plus 8 hertz. I will explain this here. Consider iron 57 in the crystal lattice which act as source. It has two energy levels. E1 is the ground energy level, E2 is the excited energy level. Then the emitted gamma ray ES will be E2 minus E1. Consider iron 57 in a different lattice, say steel. Then the lower level will be E1 prime, higher level will be E2 prime. Both level will get shifted by some amount. Then E absorber is equal to E2 prime minus E1 prime. The difference between these two, this EA and ES, difference between EA and ES is delta and is called isomer shift. If both the ion are in the same environment, then this shift will be zero. Depending on the environment of ion, there may be a shift that is called isomer shift. And this isomer shift is usually of the order of 10 raised to 8 hertz. In the terms of energy, it is of the order of 10 raised to minus 8 electron volt. This shift is large compared to the line width of gamma ray. Okay, so there is no possibility of resonant absorption. I will explain that using this figure. Your original gamma ray, which is emitted, is of the order of 3.5 into 10 to the power 18 hertz. So this is roughly 3.5 into 10 to the power 18 hertz. And it has a line width of 10 to the power 6 hertz. So this is a broad end one. The width is 10 raised to 6 hertz. But even if you make the recoil very small or recoilless absorption peak will be shifted by maximum of 10 to the power 8 hertz. The broadness of the original peak is only 10 to the power 6. The shift due to the different chemical environment will be of the order of 10 to the power 8 hertz. Now, if there is a recoil, with the recoil, the shift can be around 10 to the power 12 hertz. Okay. Initially, we discussed the maximum shift due to recoil can be around 10 to the power 12 hertz. If we reduce the recoil, still there will be a shift of around 10 to the power 8 hertz due to the different chemical environment. Then also there is no chance of a resonant absorption. Okay, because the emitted gamma rays of this frequency, and in order to absorb that is in this range, that these two are different by around 10 raised to 8 hertz. Okay, so in order to get a resonant absorption, what we can do is, again, we can use Doppler shift. Earlier it was a nuisance, but here Doppler shift is useful for us. What we can do is vibrate the source with a maximum velocity of around 1 centimeter per second. Okay, you vibrate oscillation. At extremum, the velocity is 0. When it passes through the equilibrium point, maximum velocity is 1 centimeter per second. Okay, 1 centimeter per second. A 1 centimeter per second velocity can produce a Doppler shift of 10 to the power 8 hertz. Calculation is same as earlier, 10 to the power 8 hertz. Okay. So, during a vibration, velocity will vary from 0 to 1, and in the opposite direction, it can go maximum of -1. So when the velocity vary from 0 to 1, your Doppler shift can vary from 0 to 10 to the power 8 hertz. So it can scan a range from 0 to 10 to the power 8 on both sides. It can scan a range of frequencies from 0 to 10 to the power 8. Okay, so here is the picture. If the velocity is 1 centimeter per second, then this shift is 10 to the power 8. When velocity is 1 millimeter per second, it is of the order of 10 raised to 7. When the velocity is nearly 0, then these two will come close to it. So according to the motion of this source, you can have a Doppler shift, a maximum Doppler shift of about 10 to the power 8 and a minimum of 0. Okay, so how can we get a spectra? This is the source which is vibrating. This is the absorber. If the source is not vibrating, source will produce radiation, gamma ray radiation around 10 raised to 18 hertz. But due to the different chemical environment, the absorber need radiation which is different from 10 raised to 18 hertz by an amount, say 10 raised to plus 8 hertz. A shifted frequency is needed in order to get absorbed by this absorber, because the chemical environment of this absorber is different compared to source. The source is emitting a radiation of 10 raised to 18 hertz, but the absorber need a shifted frequency. How can we obtain that shift? You vibrate the source. While vibration, the velocity varies from 0 to a maximum. Then the Doppler shift also varies from 0 to 10 to the power 8 hertz. So when the absorber sees a frequency matches with this one, then there will be absorption. So if you plot a graph with velocity on the x-axis and intensity on the y-axis, you will get a peak, a reduction in intensity at a particular velocity. That is, at this velocity, your Doppler shifted frequency matches with the absorber energy level shift. Then there will be absorption of this gamma ray, and the intensity of gamma ray will reduce at that particular point. After that, it will again reaches to 100%. Okay, so this reduction at a particular velocity, from that velocity, you can calculate what is the corresponding shift. Okay, this is the principle of Mossbauer spectra. This is the principle of Mossbauer spectra.